2022 question number 4. This is an absolute shocker of a question. One of the all-time most disgusting, top five least favourite Olympiad questions. If you're here for this video, you're probably here for part E. You're probably here for part E, but let's just quickly run through. We've got a lot to say about part E and part F, but let's quickly run through the first part of the question, which is okay. So we have a lateral flow test, which let me think. Would you all be? Yeah, you should all be familiar with lateral flow tests still. I guess there will be a point eventually where people won't be so familiar with them. A swab is taken and placed in a 1 centimetre cube extraction solution containing 7.3 millimoles of this salt and 4.6 millimoles of this salt. And what is the purpose of the chemicals? So it should be just quite clear from your general knowledge that we've got HPO4 2 minus and H2PO4 minus, and we're going to be setting up. These are roughly not quite the same, but they're quite similar, and that's going to be setting up an equilibrium. And the equilibrium has got fairly reasonable quantities of this and this. All right, so the conjugate acid-base pair, which means that makes a buffer solution. Okay, so buffer solution, nice and easy. Then, if 1 centimetre cubed of 0.1 mole per decimetre cubed HCl were then added to the extraction solution, what pH would the result solution be? So the temptation here is to think, well, it's a buffer solution. We know that the pH of the buffer solution is 7.4. We know that it's going to resist changes in the pH when an acid is added. But the point here is that this amount of acid is just huge compared to this. Okay, this is 7.3 millimoles in 1 centimetre cubed. This is 0.1 moles in 1 centimetre cubed. So this is the same volume, but the concentration is like several orders of magnitude larger. So it's definitely just going to make it acidic. Buffer solutions aren't. They resist changes in pH within a range, right? But once you add loads of acid, and you'll know that because you'll know that the pH curve, if you do a neutralization, we sort of have the buffer region, all right? But once you get too far this way, you're no longer in the buffer region. So we're going to be making it very acidic. So during the test, the person swabs their nose and throat, nose or throat, and places it in the extraction solution. The resorting solution is called the test solution. A test sample of a few drops of the test solution. Test sample of the test solution. It's already annoying me. It's so complicated. If the person taking the test has the COVID-19, there will typically be this many virus particles per centimetre cubed in the test solution. Each virus particle has approximately 20 spike proteins on its surface. What is the concentration of spike proteins in the test sample placed on the pad in moles per decimetre cubed? Alright, so it's a unit conversion question. Fine. Alright, so I've got 7.1 times 10 to the power of 6 virus particles in 1 centimetre cubed. So the first thing I'm going to do is I have to times by 20 because each virus particle has approximately 20 spike proteins. Okay, so we're just going to go 7.1 times 10 to the power of 6 multiplied by 20 gives me 1.42 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8 spike proteins in 1 centimetre cubed. And now the only task is then to convert that into moles per decimetre cubed. Okay, so that should not be too difficult. In order to do that, we're going to have to divide by Avogadro's number to convert it into moles. So this is a number of particles, and I want the moles of particles, so I divide by Avogadro's constant. And then I have to put it into decimeters cubed. So in order to put it into decimeters cubed, I just need to think, well, how many centimeters cubed are in a decimeter cubed? There are 1,000, so there's going to be 1,000 times more in a decimeter cubed. So I times by 1,000 and I divide by Avogadro's number, and I get 2.36 times 10 to the minus 13 moles per decimeter cubed. Fine. Okay. Now, again, so it's going to start getting more difficult. Really, you want to have had a go at this question yourself, so you're familiar with it, because it's a really complicated question, and if you're not really clear about what's going on, it's not really make much sense. So once the sample passes the conjugate pad, so you put the sample in here, you drop the sample in here, and it goes along here towards the test line. Once the sample passes the conjugate pad, it becomes saturated with red-coloured antibody-coated gold nanoparticles, up to a concentration of 1.6 times 10 to the power of 12, which is a pretty large concentration. An equilibrium is set up where the nanoparticles, so those are the gold nanoparticles, bind to any spike proteins, assuming that any binding that takes place between the spike proteins and the nanoparticles is 1-to-1. So the spike protein, the nanoparticle, gives me this spike protein nanoparticle. All right, and I've got this equilibrium constant here. Fine, no problems there. Then it says, as there is a large excess of nanoparticles, yeah, we already said that this was quite a large number, you can assume that the concentration of nanoparticles at equilibrium is still 1.6 times 10 to the power of 12. Determine the concentration of the spike particle nanoparticle combination at equilibrium in moles per decimeter cubed. Okay, fine. So let's see if we can do this. So I'm going to write it out myself. SP plus NP. So my spike particle, my gold nanoparticle, gives me my spike protein nanoparticle bound together. Fine. And then I know that the initial concentration of this is what I just worked out. So 2.36 times 10 to the minus 13. Fine. I know my nanoparticle concentration, and this is number one annoying thing about this question. Number one, what is the concentration of the nanoparticles? Oh, well, look, it's just 1.6 times 10 to the power of 12. Wrong. It's not 1.6 times 10 to the power of 12. Well, it is, but that's particles per centimetre cubed. But I need this to be done in moles per decimetre cubed. So there is a secret hidden unit conversion here. I need to turn my 1.6 times 10 to the power of 12 NP per centimetre cubed into moles per decimetre cubed. It's just a secret bonus one for you. Okay, so I do that the same way I did this one up here. So I'm going to do 1.6 times 10 to the power of 12 times by 1,000 divide by Avogadro's number to give me 2.66 times 10 to the power of minus 9. 2.66 times 10 to the power of minus 9. Okay, and then this initially is 0, and then it says that, well, so what's going to happen then is you're going to obviously consume this, and make this as the equilibrium proceeds. So we're going to get 2.36 times 10 to the minus 13 minus x. This is going to be the number of spike protein nanoparticle combinations is going to be x. But then it says in the question, you can assume the equilibrium value of this hasn't changed. So he's going to leave that in 2.66 times 10 to the minus 9. Fine. Okay. So then I just put it all into my equilibrium expression. So it's going to be x over nanoparticle 2.66 times 10 to the minus 9 multiplied by 2.36 times 10 to the minus 13 minus x equals 1.2 times 10 to the power of 10. Okay? And then you just solve for x, which is a little bit boring. I guess if you can use the solve function on a computer or a calculator, it's probably quite straightforward. I'm just going to do it. I'm not going to make you sit through it. Okay, so I've multiplied it out a little bit. So from here I can just solve for x, because this is going to be 32.92x equals 7.53 times 10 to the minus 12. So x is going to be 7.53 times 10 to the minus 12 divided by 32.92. Gives me 2.29 times 10 to the minus 13. Okay, and that all makes sense because this was given as moles to the minus 1 decimeters cubed, and this I had everything in moles per decimeters cubed, so this comes out as moles per decimeter cubed. Fine, no problems there. All right, then the resulting mixture flows over the top, flows over the test strip, which contains surface immobilized antibodies. God, this is so complicated. So we have the spike protein, then the spike protein bonds to the gold nanoparticle, and now it's going to bond to the surface immobilized antibodies. All right, so super complicated. You know, you maybe draw yourself a diagram or something so you understand what's happening. When considering the amount of a substance on a surface, we use surface density instead of concentration. Fantastic news. The test strip is 3 millimeters long, 1 millimeter wide, and 0.1 millimeters deep, with a surface density of antibodies of this. Calculate how many surface immobilized antibodies there are on the test strip surface. Well, it tells me the surface density of antibodies is this number, and it tells me that it's 3 millimeters long, 1 millimeter wide. So the surface of the strip is 3 millimeters squared. So this is just ridiculously easy now, because it is 1.2 times 10 to the power of 9 per millimeter squared multiplied by 3 millimeters squared, which I don't even need my calculator. Me. 3.6 times 10 to the power of 9. All right. That's how many there are in that area. Then it says, calculate how many free spike proteins and how many nanoparticle bound spike proteins are present in a volume of solution of the size of the test strip before any interaction with the test strip. So, this is where it starts to get even more confusing. I can't say starts, because I'm already confused about everything. All right, so let's be really clear. A volume of solution of the size of the test strip. So the test strip is here. This is where I'm told about the test strip. So the volume of the test strip is 3 times 1 times 0.1, which is 0.3 millimeters cubed. Okay, and it wants to know how many spike proteins and spike protein nanoparticles are there in 0.3 millimeters cubed. Well, that's okay, because I already know what my concentrations of those two things are. So what I need to do is write out SP concentration and SPNP concentration, and then I know the volume of my test strip, so if I know my concentration, I should be able to just work out how many particles are in that volume. So it's a pretty straightforward question. It's just taking the concentration and working out in 0.3 millimeters cubed how many particles are there. So again, we're going to do a unit conversion. But, and I've done this question a number of times over the years, and quite a few times in recent memory. And the one mistake I always make is when I write this out, I go, well, okay, well, I just worked this out up here, right? This question was calculating the concentration of SPNP. So I can write that down as 2.29. times 10 to the minus 13 moles per decimeter cubed. And then the mistake I always make is I go here and I write out, well, I know this one is 2.36, but it's not 2.36. It's 2.36 minus x. So easy mistake to make again. So this is 2.36 times 10 to the minus 13, subtract the value of x that we calculated, 2.29 times 10 to the minus 13. Okay, remember, because this value is the original value of the spike proteins, but once you put the into the nanoparticle mixture, all right, and that's what we're concerned about, you have to subtract this from our equilibrium calculation up here. So that's going to give me 2.36 times 10 to the minus 13 minus 2.29 times 10 to the minus 13 is not that. Right, let me just have, I've missed out my, typed it in wrong. 2.36 times 10 to the minus 13 minus 2.29 times 10 to the minus 13 gives me 7 times 10 to the minus 15. Okay, fine. So that's my concentration, but both of those are in moles per decimeter cubed. Now I want to know how many there are in 0.3 millimeters cubed. So I need to convert my moles into particles. So I'm going to multiply that by Avogadro's number. And then I need to do this. This is a really ugly unit conversion. So we're going to go from per decimeter cubed to per millimeter cubed. Now, for some reason, I mean, unit conversions don't usually upset me too much, but this one, for some reason, really gives me a little bit of grief. So let's just, I need to be going, so I've got this many in a decimeter, but I've got 0.3 millimeters cubed, which is obviously much less than a decimeter cubed. So let's work it out. Well, I know that 1 dm is 10 centimeters, and I know that 1 centimeter is 10 millimeters. So that's 100 millimeters. So 1 dm cubed, a litre, is 100 millimeters all cubed, which is 1 times 10 to the 6 millimeters cubed. So that's the number of cubic millimeters I have in a cubic decimeter, which means I can do the inverse of that, which means in that 1 millimeter cubed is 1 times 10 to the minus 6 decimeters cubed. And then I can multiply both sides by 0.3. Okay, so 0.3 millimeters cubed is 0.3 times 10 to the power of negative 6 decimeters cubed. Okay, so I don't have a decimeter cubed, I have a 0.3 millimeter cubed. So I'm going to multiply this by 0.3 times 10 to the minus 6. Now that, for me, I'm sure there's an easier way of doing it that makes a little bit more sense. I very rarely do a unit conversion and feel this unsure about it. But there is one check I would always do, and the check is to think, all right, do I need to be making this number bigger or smaller? So if this is the number in a litre, in a decimeter cubed, remember a decimeter cubed is a litre, if this is the number in a litre, and I want to know the number in 0.3 millimeters cubed, this is obviously much smaller than this. So I should be either dividing by a big number or multiplying by a really, really small number, which I am doing here. Okay, so I'm okay with it. So I'm then going to do that times Avogadro's number times by that, and I get 1264. 1260. And then I do the same thing here. Multiply by Avogadro's number, multiply by 0.3 times 10 to the minus 6. So I get 2.29 times 10 to the minus 13 times by that times by that I get 414,414,0,0. Okay, and that's it. And then the question ends, or at least you wish it had ended, because now we go on to this. The surface immobilized antibodies AB bind to any spike protein present, free SP and nanoparticle bound SPNP with the following equilibria. Fine, okay, so the antibody can bind with the spike protein, the antibody can bind with the spike protein nanoparticle combination. All right, and they have the same equilibrium constant. All right, fine, I don't mind. Then, determine the number of nanoparticles immobilized on the test strip. AB, SP, NP. Once the whole 0.1 centimeter cube test sample has fully flowed past. Okay. So it seems like it's going to just be a straightforward equilibrium question. All right. However, there's a few things that are going to really, really trip us up. The first is this is a concentration. These are surface densities. Okay, that's not a problem. The surface density is just the number divided by the area. So number divided by area, number divided by area, concentration. So the units for these cancel out, which is why I end up with this inverse concentration unit here, because I've got the concentration in the denominator. So first thing for us to understand is fine. Now the second thing, and this is honestly the level of complexity in this question, I really, I think the questions they make are great. I think this one, it just went a little bit too far. So the problem is, you're given the whole 0.1 centimeter cube test sample, all right, but we're talking about on the test strip. Okay, so we've got the test sample and we've got the test strip. Now, the volume of the test strip is 0.3 millimeters cubed. The volume of the test sample is 0.1 centimeters cubed. So that's also just worth bearing in mind. Okay. Now, I have done this question many, many times. I've done it many times unsuccessfully. On this occasion, obviously, before I make any of these videos, I have to do the question right before I do it, so to remind myself of it. And this question, this is the working from my attempt at this question most recently. All right, just pages and pages and pages where I get through to a certain point and realise I've made a mistake, get through to a certain point, realise I've put the wrong number in. It just gets complicated. So this is, after much reflection, the way that the question makes sense to me. So I'm going to write out my equilibrium expression. K equals, now it's asking me about AB, SP, NP. So this first equilibrium you're given, just ignore it. No one cares. No one cares about you. No, I'm going to cross it out. Go away. And I'm going to cross this out. You can go away as well. So what I've got is I've got the surface density of AB, SP, NP divided by the surface density of AB multiplied by the concentration of SP, NP, fine, equals 3.3 times 10 to the power of 10 moles to the minus 1 decimeters cubed. And it's asking me to find the number of AB, SP, NP. All right. Fine. Okay. Let's write out our equilibrium. AB plus SPNP in equilibrium with AB, SPNP. And it's just going to be the same thing again, right? As long as I know the number of this and the number of this, there's 0 of this to start with, I'm going to consume one of these, and make one of these. So it's going to be minus x plus x. Fine. So, do I know the number? Now remember, I want to go, I can't say here concentration, because this isn't a concentration. So when I did the other one, back here, When I did this one, I was dealing in terms of concentrations. Now I can't do that. So what I'm going to do, and this is something that just, for me, it just makes me a little bit happier, is I always just go and think, okay, let's just go right to just the number of particles. Usually I would do the number of moles. But on this occasion, we're just going to say, all right, what are the number of particles? Because that's what I need to find out in the end anyway. So I'm not going to go to moles, I'm going to straight to particles. So what are the number of particles of AB on the test strip? Now, luckily, we calculated that in E part 1. Okay, so the answer to E part 1 goes here, which is 3.6 times 10 to the power of, just reading it off my other piece of paper, 3.6 times 10 to the power of 9. Oops. Fine. Now, if I need to do this, if I'm not going to do it in terms of concentrations, if I'm not going to do it in terms of moles, if I'm going to do it in terms of number of particles, that means that everything has to be in terms of number of particles. So this is where it really gets ugly. Again, what is the number of particles of SPNP? Well, I know the concentration of SPNP, in theory. I know the concentration. See, this really confuses me a lot. So if I've got back here in E part 2, I've got this calculation. I've got SPNP, okay, as this concentration, and then I converted it into a number of particles. So the temptation now is to take 41400 and write it there, because that's what I did back here, right? E part 2 says calculate how many nanoparticle bound spike proteins SPNP there are. Okay, and that's what I need to put into this equilibrium. However, the confusion is that in E part 2 you were asked to calculate the number that are present in a volume of solution of the size of the test strip. But here we are doing a 0.1 centimeter cubed test sample. Now, again, this video is going to be very long because we still haven't got to the bit where I just moan endlessly about this question. But that's something that confused me for a really long time, is that here you work out SPNP number of particles if I had a volume of this size. But I'm passing a volume of 0.1 centimeters cubed. So what I need to do is I need to work out how many there are in 0.1 centimeters cubed. So the number of SPNP in 0.1 centimeters cubed. Right? So if my concentration of SPNP is 2.29 times 10 to the minus 13 moles per decimeter cubed, then the number of SPNP in 0.1 centimeter cubed is going to be 2.29 times 10 to the minus 13. Oops, 2.29 times 10 to the minus 13. Multiplied by 0.1 divided by 1,000. That's my volume conversion. Multiplied by Avogadro's number. Gives me this number. 1.38. 1.38 times 10 to the power of 1, 2, 3, 4, 5, 6, 7. And this is 0. Obviously at this point, if you've had enough, just don't do this question. Right? Like, there's absolutely no need to do this question. But let's carry on. So then I do 3.6 times 10 to the minus 9, times 10 to the 9 minus x, 1.38 times 10 to the power of 7 minus x, and then this is x. Now, solving that should just give you the answer, right? So if I do x divided by 3.6 times 10 to the power of 9 minus x, 1.38 times 10 to the power of 7 minus x equals 3.3 times 10 to the power of 10. X equals, now I put it into a obviously you can do it by hand, or I put it into a thing on the internet to solve it for me, and it gave me 1.38 times 10 to the power of 7. Okay, which is the correct answer. Fantastic. Okay, but there's a few things. Obviously this number is the same as this number. Okay, and it's worth thinking about that, all right, because there is an easier way to do this question, and I believe, let me just check the mark scheme. Just double check. Now, the correct answer will get you all 3 marks. So if we just go back here, okay, so the thing that you can realise is that this number here is massive. That's a huge. Well, it's not huge, but it's a fairly large equilibrium constant. So what that means is that all of this equilibrium is going to happen, right? And I know that I've got 100 times more, or 300 times more antibodies than I have spike protein nanoparticle things. Okay, so I've got 3. This number is times 10 to 3 times 10 to the 9. This is 1 times 10 to the power of 7. So I've got 300 times more of these than I have of these, and I've got a massive equilibrium constant. So what that means is all of this is going to get consumed, and that's why X comes out as the same value of this. It means that this number here goes almost to 0. Right? Now, I don't know. I mean, you have to be, maybe in a time constraint, you could just write that down and hope for the best. But that's the other way that I thought about it. Now, the final thing for me to say about this, no, I've got 2 more things to say about it, is we have the method they give you in the mark scheme, which, fine, if you follow it yourself, that's great. I'll just talk about it for a second. Okay, so if Y SPNP bind to AB to make Y AB SPNP, then we have the concentration of SPNP is so after this binding has happened, is the original concentration minus the concentration that have now been bound. Okay, which is why it's Y over V, because this is a concentration. So it's the initial concentration of SPNP minus the so the number of SPNP, so the concentration of SPNP remaining is the initial concentration of SPNP minus the concentration of SPNP that have been bound. Fine. And then we have the surface density of AB SPNP is Y over A. Great. Okay, and then this is just from the equilibrium constant calculation. Okay, so they've just multiplied up the concentration of SPNP. Then they've multiplied in the area, multiplied by 1, A over A. Fine. And then they've substituted sigma AB SPNP for Y over A. So that cancels the A at the top. And then they've substituted in SPNP for that, and they've rearranged it to get this, and then they've made this identification that this is much, much larger than 1, so you can ignore it. Now the problem, fine, you do it and you get the same number. Fine. The problem I have with this, and I think this is one of the reasons it's not a great question, is that there's just no way, without knowing beforehand. Like, I can read this and I can understand what they've done, but to come up with these 2 substitutions myself is a big ask. All right, and I really think that that it's very unlikely that anybody in a test situation under a time constraint on a difficult test is going to think to themselves, "Oh, I know what I'll do. I'll make this substitution so that I can put it in later, and I'll make this substitution so I can put it in later." It's like, if you know this method, fine. If you've studied this method in a textbook and apply it to a different situation, then fine. And that is why if I go to the examiner's report for this question, it says, this question was very difficult. Right, yeah, no kidding. Most students did not score marks other than the first couple of parts. It was pleasing that students recognised that this was a buffer, the first mark out of 13, and some realised that the buffer was used up by the amount of acid. So some got the second mark out of 13. After this, the students struggled. And then importantly, this is what they say, in the scripts moderated by the working group, we did not see a fully correct solution to some of the more difficult sections, such as part F. So in other words, nobody got this question right. Okay, so that's that. Then, that's the end of my discussion of that question. The visibility of the test line depends on the number of nanoparticles which become immobilized on it. Nanoparticles are visible down to a surface density of 3 times 10 to the power of 6 nanoparticles per millimetre squared. And it asks you, determine the minimum number of virus particles present in this test sample which would give a positive result. So again, this question took me much, much longer than it should have done to really work out what it was asking. So we start with the virus particles. And the virus particles give us, at the end, the ABSPNP. Okay? And I've just worked out somewhere, where's my answer gone? That my number of these is 1.38 times 10 to the power of 7. Okay, and the area of that is in 3 millimeters squared. Okay, so my density, my surface density, is 1.38 times 10 to the power of 7 divided by 3 gives me 4.6 times 10 to the power of 6 per millimetre squared, which is larger than the minimum. Okay, but we want to know what's the lowest number of these we could have had. Well, how many of these did we have right back at the very start of the question? Well, if we go all the way back to the start, we go all the way back to the very start, we were told there will typically be 7.1 times 10 to the power of 6 virus particles per centimetre cubed in the test solution. But remember, we want the test sample. Honestly, the level of difficulty is, you have to. It would take the entire time of the test to really be able to analyse the language in the question to understand exactly what they're asking. So a test sample of 0.1 centimetres cubed is placed on the sample pad. So I don't have 7.1 times 10 to the power of 6 virus particles. I've got 7.1 times 10 to the power of 5 virus particles. Okay, so 7.1 times 10 to the power of 5 gives me this density. This is the smallest density that it will work for, so I can just do 3 times 10 to the power of 6. That's my minimum number. Divided by 4.6 times 10 to the power of 6. That's my actual number. Multiplied by how many I started with, 7.1 times 10 to the power of 5. So if I do that, it's going to be 3 divided by 4.6 multiplied by 7.1 gives me 4.63. 4.63 times 10 to the power of 5 virus particles. And that is the end of that question. I never want to have to think about this question ever again.